The next speaker is David Gleich from the University of Purdue University. As I would like to also remind for those who just joined that we are you can share your questions on the chat. So just please write down questions there. We will have a question and answer session at the end of the presentations. And yeah, please, David.
All right, thanks. We're going to have some fun here. And am I sharing my screen? No, I'm not. Let me do this.
No, not yet.
Okay, it should be starting. Okay.
Yes.
Yes. Okay, so we are gonna watch some pre-recorded videos, and these are all available online too. So if anyone is having trouble watching them through here, I'll send out a link in the chat soon. I just want to do a bunch of things that I couldn't do live, as you'll see shortly.
Oh, hey there. How's it going? Yeah, it's definitely an interesting year this year, isn't it? A lot of new stuff going on. How about these virtual conferences? You know, I guess I'm in a similar boat. There's always too much to watch and never quite enough time. Oh, what have I been working on? Oh, that's actually interesting, right? I guess we don't get to go around and give these elevator pitches like we usually do. So let me tell you, I guess. So I think the thing I'm talking about in a little bit is this idea we call nonlinear processes on graphs. And the idea is you can take PageRank and other spectral graph-like algorithms and throw just a small nonlinearity into it. And what comes out is a lot of times you can get some better results on a lot of problems like semi-supervised learning and a whole bunch of other stuff. And now there's always more trade-offs with nonlinear things, but I think there's some cool opportunities too. Lots of potential for future research, and our talk definitely has a lot of pretty pictures in it. Oh, and would you look at that? Huh, I guess my session's up next. I hope you can make it. Huh, well, you know, I guess I would probably skip my own talk for a triple Fields medalist, Turing Award winner, Nobel Prize winner as well. Anyway, these parallel schedules at these conferences are impossible. Anyway, we will definitely miss you. Make sure you stay safe. Oh, hi there. How's it going? In case you didn't get it from the intro video, I am not going to give a standard voiceover talk where we have some slides and then we go over I narrate through the slides as I would do in the standard presentation. We're going to have a little bit more fun. Any feedback on this type of talk would be appreciated because, as I mentioned, it's an interesting year. And so it's a good excuse to try something new, I thought. Okay, and as you saw in the prologue, what we're going to talk about today are nonlinear processes on networks. Let me tell you about a little bit more about what I mean by that. Okay, now one other note for all you folks over here. It's pretty bad form to introduce something by telling you what it's not as opposed to what it is. So to cut through the chase here, what I mean by a nonlinear process on a network is simply we're going to take a linear process on a network and just throw a small nonlinear function on it somewhere. It could be a power function like x to the 1/2, or it could be a log transform or a tangent or something, but we're not talking about massively changing the linear structure that you're used to. We're just adding a little bit of a tweak to it. Linear processes on graphs are probably something that you've run into before, and for a variety of reasons, one of my favorite examples of this is the PageRank process. The way I like to think about PageRank is as a process that takes information from a seed set of vectors and moves it across the graph onto all of the vertices or nodes of the graph. That is, it takes the information from the seeds and diffuses them across the entire network. Now, we usually think of PageRank as starting with a set of seeds and moving that information across the graph, but you could use any non-negative vector of information, weighted, anything else that you want to put in there, and the mathematics of PageRank largely go through for that as well. PageRank, of course, is a linear operator. And so what that means is if you have a linear combination of seeds, you get a linear combination of PageRank vectors. And we can write that in a couple of different ways. We can write it mathematically, or we can just draw a picture of it. Now, linear operators are really awesome, and they've been responsible for a tremendous success of research in graph theory and different ideas in network analysis. And one of the reasons for that is linear operators are really exist at the nexus of a whole lot of different ideas. We can derive or state PageRank from a number of different perspectives. It's from Markov chain theory, from dynamical systems theory, from smooth functions on graphs, from matrix function theory, from maximum likelihood estimate on stochastic block models, and many, many, many more. There are continually new perspectives on PageRank that emerge, and this single algorithm exists at the nexus of all of them. When you think of a PageRank algorithm, you can think of just running the simple linear diffusion from seeds to solutions, but implicitly what you're doing there is you're running a whole host of different algorithms, all of which have slightly but closely related interpretations. So why am I spending all of this time talking about linear processes on graphs when the title and the subject of this talk is our nonlinear processes on graphs? Well, the reason I mention all of this is because when you apply a small nonlinearity to any of these derivations, all of those equivalences break. So when we talk about nonlinear processes on graphs, we need to start from one of those different perspectives and put the nonlinearity in a natural place in that perspective. If you apply a small nonlinearity, say take a power iteration that's been inspired by Markov chains, and just apply a small square root function at every step, then we lose the vast majority of those equivalences. What this means is when we do these nonlinear processes on graphs, it's important to fix ourselves in one of those many different interpretations of PageRank and apply that nonlinearity in a way that makes sense for that particular interpretation. What I'm going to tell you about today are a few of the ideas we've been working on in this space, where we'll take one of the interpretations of a linear process on a graph, case in point, PageRank, and then we're going to apply a small nonlinearity at some point. And we're going to see some of the trade-offs and advantages that result from that transformation. This involves a whole bunch of projects I've been working on with some very talented students recently. I really wish the students could be here to tell you about this themselves, but it's not as easy as it might seem. A lot of them are away on internships and other types of activities right now. Let me also reiterate that there's others working in this space too, including some of the mini symposium organizers. In a project on nonlinear diffusions with Rania Ibrahim, what we did was we took a dynamical systems perspective on some of these graph diffusion processes, and we just put a little p-norm or a p-Laplacian function as the transfer function. Essentially, we put this into the derivative function of the dynamical system underlying these diffusions. And what this allowed us to do was to get a lot more interesting results that was competitive or actually exceeded some of the performance of neural network models or some of these graph convolutional networks that people had developed. In the glance method with Huda Nassar, Shweta Jain, Caitlin Kennedy and Austin Benson, what we did was we took a nonlinear transformation of the adjacency matrix itself, and then we did a whole bunch of spectral methods. Now, the inspiration here actually came out of some work that's in our hypergraph methods, where you use a clique expansion of a hypergraph in order to do things. What we did in the glance method was we did exactly that, but we sort of viewed this as a nonlinear transform of the adjacency matrix. And so we were able to put in a set of custom weights that wouldn't have followed exactly from what the hypergraph methods would have suggested. This just gave us a number of opportunities to develop a visualization algorithm that makes nice looking pictures of graphs. We then demonstrate this by showing that the pictures of graphs that we identify have different trade-offs with respect to which ground truth topological properties they preserve compared to other ways that people have drawn pictures of graphs before. In one of the other projects we've been working on recently with Kimon Fontelakis, Meng Liu, and Michael Mahoney, what we've done is we've taken a look at all of the literature on minimum cut and maximum flow-based cluster improvement. Now, in max flow min cut cluster improvement, what you do is you start from a reference graph and you improve it into an improved cluster S. And we'll see some examples of this in one of the future videos. But you can relate that back to you can actually derive PageRank-like methods from taking that same methodology and applying a 2-norm operation somewhere. The min-cut max-flow operations correspond with a 1-norm version of that same type of methodology. Now, one of the things that we struggled with that min-cut max-flow technology is that the output is always discrete from that. You always get a 0 or a 1. Whereas with linear operations like PageRank, what you get is a real valued vector that allows you to sort the values meaningfully. It allows you to threshold at various levels. It allows you to study gaps in those vectors and all sorts of other useful things when you're talking about downstream applications. One of the things we like about the spectral methods is that you can do little local visualizations of the network. You can meaningfully use either eigenvectors or PageRank vectors in order to get local embeddings of the nodes. Using these flow techniques, we didn't see a way to do that. However, what we figured out was that you can use a sort of randomized or expectation perspective on what you get out of a PageRank vector, and then you treat this as a process from input to output, and you use an SVD, and you can get a lot of similar things from these discrete 0-1 vectors that give you a very different style of visualization for a local part of a network. Just to cut to the chase, it tends not to look at the manifold structure like you get out of the 2-norm spectral methods. What it really does is it preserves cluster structure. So if you think that your graph has a lot of sub-cluster structure, this might be far more appropriate than some of the manifold structure methods based on PageRank. In another project that sort of naturally follows from the flow-based one, and this is with Meng Liu, what we did was we said, okay, well, if PageRank corresponds to a 2-norm problem and these max flow min cut problems corresponds to a 1-norm problem, there's a family of things in between that are based on p-norms. And using those, we can get all sorts of really neat algorithms that have some of the advantages of the flow methods. That is, one of the classic things that the flow methods do better is they track boundaries much more sharply than the spectral or 2-norm methods do. But one of the challenges with the flow-based methods is that they have trouble expanding from a single seed node. So in general, the flow-based methods need a really large region of the graph to refine, and that's actually due to some of the downsides to the flow-based theory. But what you can get with these p-norm methods is actually something in between. And we've actually been able to come up with a whole host of different algorithms that are really neat, simple generalizations of PageRank style algorithms, but that apply to these nonlinear p-norm functions as well. If you're familiar with something called the Anderson-Chung-Lang push method for personalized PageRank, or you simply sort of understand what Gauss-Seidel would do on a coordinate basis for solving a PageRank vector, what we can do is we can solve these p-norm diffusions. We just change the simple closed form update into a bisection search instead. Now, so far we've just seen a teaser over some of these results. There are definitely some challenges with using these different methods, and it's by far from a solved problem. The algorithms have different types of trade-offs. Parameters may be easier or harder to set depending on how you do it, so it's definitely a space where we need better ideas. And let me just say that the linear graph algorithms out there are actually really good, so they make a hard benchline or baseline to compete again. The key thing with all of these nonlinear methods, though, is we don't get trivial combinations of seeds. Or sorry, simple linear combinations of seeds. All of these have the property that linear combinations do not give us linear combinations of the output. This is going to offer us some interesting opportunities, and so we're going to investigate those over another set of videos. Yes. So if you're interested in talking more about these, please let us know, and we'd be happy to chat more.
Okay, I'm going to pause there. I've got another video after this, but I wanted to give anyone a chance to ask any questions just really briefly before we jump into and do a deep dive on one of the other ideas I mentioned there.
We are going to have some fun here and show what it looks like to develop the code for a number of examples of using a simple SVD to visualize a nonlinear process. The process we're going to use is this thing called local flow improve, which takes a reference set and moves it to an output set. But this is a nonlinear process, so adding reference sets does not add the outputs. Moreover, the output from this is fundamentally 0, 1 or discrete, which makes it challenging to use it for visualization. PageRank actually works better here. So what can we do? Okay, so what we're going to see now is essentially me walking through developing all the code that goes into this next little bit of the presentation. And the fun part about this is you're going to see it in very fast, or in a greatly accelerated version. And the point of this is just to show you what actually goes into these. All the code is up on GitHub, so if you do want to check it out, you can check it out there. And you'll get to see how it's developed here live. I would recommend watching it slowly for that. All right, so first up, let's get those eigenvector embeddings done and just make a whole bunch of notes on what we're trying to accomplish here. So our first observation is that the spectral structure really doesn't actually do much in this particular case. It doesn't show us those text or the P. The second observation is that we can use Chung's local Dirichlet eigenvector embedding to actually show the local structure of that P if we already know where it's there. Our third point is really that local flow improve is a nonlinear process. You can't use simple 0, 1 embeddings to get good pictures of this. So what the heck should we do with it? Let's do some math. Okay, the idea here is that PageRank is linear, and what we're going to do is we're going to look at what impact being linear has on a notion of sampling PageRank vectors from a set. And since PageRank is linear, the expected PageRank of a sample from the set is exactly the same as PageRank on that set itself. This suggests just doing a Monte Carlo approximation ought to give us mostly the same thing. Now, the reason that Monte Carlo is actually somewhat interesting is that the average of a matrix of these, where every column is one of these samples, is actually going to be closely related to the dominant singular vector of the matrix of samples. Now, this is not a precise relationship, although some people, such as Paul Constantine, a friend of mine, have done some analysis of this, as well as others. Okay, so this actually suggests that we should just use that SVD of X as PageRank vectors or as embeddings themselves. And this can be done even for nonlinear processes. That's the key idea. So here's the algorithm. Pick a vertex, run the nonlinear process from that vertex, put that into a sample of the matrix, do that some number of times, and then do an SVD. For PageRank, this basically gives us the same thing as we get from local eigenvectors, although you can tweak it up by using some orders instead of other things. And it also gives us interesting structure for these nonlinear processes too, especially when you use the order induced by the singular vectors, not necessarily their value. We can use the same idea in other places like the US highway network on the West Coast to show on the left manifold structure from spectral methods or cluster structure from flow methods. And we can try this in one more place on the fashion MNIST dataset. Now, this is a fun dataset where it's got 60,000 pictures. Every picture is in one of 10 classes, and every class is an article of clothing. So this is meant as an analog of the MNIST dataset, where the classes were individual handwritten digits. In this one, they're all clothing. And so here we use this on the class of shoes in order to get a spectral versus flow taxonomy of shoes. All right, so let's go through this once more time. Spectral techniques largely look great, although they oftentimes miss some elements of local structure compared to global structure. These eigenvector techniques are super useful in a variety of different settings. Nonlinear processes do different things than these linear processes. In particular, they give us discrete 0-1 valued output, which makes it really challenging to use these ideas for simple visualizations where continuous ideas that would work for PageRank will not work. The key idea, again, is just that we can use a simple singular value decomposition on random samples of all of these ideas to get very similar results. And we drove this from something like expected value perspective on a linear graph algorithm, such as PageRank. If we use this on PageRank, we get back that same type of local structure, but we also get all sorts of interesting structure out of the nonlinear process as well. And there's this idea of using the order of the vector, not the actual values, to give us an even better or more interesting visualization of these. Now, of course, the idea with all of these is not to use them in cases where, like, we've got this simple nonlinear processes graph. Instead, we want to use them in really interesting scenarios. So we use this on the US road network and got a nice taxonomy by metro area. And then we use the same idea in this fashion MNIST data and got a different taxonomy. And this idea has all sorts of relationships with other ideas, including things like a POD like basis, as well as nodal embeddings of hypergraph incidence matrices. And if you know of other things it reminds you of, please let me know. For more about this, see our GitHub webpage and our paper on flow-based algorithms for improving clusters.
All right, so hopefully you can hear me again.
Yeah, we do.
Okay, awesome. I'll turn on my video in a second. So we've got time for some questions.
Yeah, thanks very much. So I wasn't sure if yeah, you had some final little thing to add, or if that was over, like the end of the talk, let's say.
That's largely it. I mean, I'm going to put up some videos on the other ones in the future. So,
okay.
You know, if you are interested in the other papers too, that would be useful. Those could be useful. But no, there's lots of, I think there's a lot of interesting opportunities in this space, and I'm looking forward to seeing what other people think about it.
Great. Yeah. So let's see. So you're in exactly the same room as the one in the video.
All right. So I've got the questions up on my phone here. So I'll go through those. So one of the questions is, how do you evaluate the taxonomies that you get, flow versus spectral? So this is one of these interesting questions. A lot of these ideas are best used for sort of descriptive or exploratory procedures. If you have some downstream application in mind, you know, of course you would evaluate it in terms of that. And so what we see on a lot of investigations of semi-supervised learning is that the flow-based techniques do have these much sharper boundaries than you get with the spectral techniques. But what we wanted to do was a way to make that easier to explain to people. And so the taxonomies that we get out of these, you know, you can debate taxonomies until the end of time. People in biology love doing stuff like that. The question is, I think the way we would suggest using these is to use them to communicate results more efficiently. This is sort of a natural way of how that particular algorithm understands that data, and that's a nice way of using it for that. Another question is, what are the techniques to prove convergence results when you go nonlinear? Great question. So one simple answer is you can avoid proving convergence results and just focus on deterministic algorithms. That is, if you have a permutation invariant input and you have a permutation invariant update, then what you get out is always a deterministic answer invariant of whether or not it converges or not. But yeah, in general, convergence for nonlinear things and uniqueness are not nearly as simple. So yeah, I know some people here working on better ideas on that kind of stuff too. So hopefully I can learn more about those in the future. Are you applying these nonlinearities in a component-wise manner, not a matrix function in sight? Oh, sorry, I've got one question left, I think. So excellent question. It depends on the particular perspective. So when we think about the paper with Huda Nassar, Shweta Jane, Caitlin, and Austin Benson, there, what we really do is we do a nonlinear transform of the adjacency matrix itself. And so the input is the adjacency matrix and the output is a modified adjacency matrix. Now, I suppose if you really wanted to twist yourself, you could call this a matrix function, or some type of really complicated matrix function, although I don't know how useful that is. But largely, some of these, so So the matrix function perspective really focuses on the linear case because the matrix is a coordinate-wise representation of a linear operator. So a lot of that technology just has a totally different interpretation from a lot of the stuff we're doing. And so the short answer there is no, but there could be some really cool possibilities there that I haven't thought of yet. So I don't want to dismiss that idea just because I don't know how to use it.
I don't know if, can you hear me?
Over time, so I don't want to keep answering questions. I'm happy to take more if people want to email them to me as well.
I don't know